In this video, the radar cross-section is described. The radar cross-section sigma, or RCS, is a specific quantity of the reflecting object that depends on many factors. When an electromagnetic wave encounters a boundary between two distinct media, such as air and water, a portion of the wave's energy will reflect back into the first medium, while the remaining part continues through the second medium. This occurrence is commonly referred to as reflection. In general, a reflecting surface is the boundary between two materials of different electromagnetic properties. There are two primary laws of reflection. First, the angle of incidence, theta I, is equal to the angle of reflection, theta R. In other words, when an electromagnetic wave strikes a surface, it will be reflected off the surface at the same angle it approached. This phenomenon is called Snell's law. Second, the incident wave, the normal to the surface. This is the blue vertical line above the point of reflection. And the reflected wave all lie in the same plane, here shown as an amber area. By the way, the beam is deflected when it enters the second medium because the electromagnetic waves propagate at a slower speed in the denser medium. This phenomenon can also occur in air surveillance radar if there are boundary layers in the atmosphere caused by different air temperatures. This sometimes results in false alarms as similar reflections can occur in dry air layers with varying densities. The echo signal received by radar is made up of reflections and components caused by diffraction, which is a unique phenomenon of waves. When a wave passes through a gap or travels around an obstacle, it spreads out. In the picture, the red color represents a wave trough, and the blue color represents a wave crest. When a wave crest meets a wave trough, the wave is extinguished. Conversely, when two wave crests or two wave troughs meet, the wave is amplified. The waves that come across a reflective object are scattered in different directions at sharp edges or peaks. Which is why the radar principle is referred to as backscattering rather than reflection. In the equation, the reflected area is the effective area that captures the incoming wave and radiates it back into space. This means that only a power density caused by the geometric area arrives at the receiving antenna. The radar cross-section sigma is defined as this geometric area multiplied by the ratio of the power densities at the receiving location to the power density at the reflector. The computational determination of the RCS is only possible for simple bodies. The RCS of simple geometric bodies depends on the ratio of the structural dimensions of the body to the wavelength. Practically, the RCS of a target depends on the physical geometry and exterior features of the reflector, the direction of the illuminating radar, the radar transmitter's frequency, and the electrical properties of the reflector's surface. The following equations for calculating the effective backscattering area apply under the assumption of optical, which means frequency-independent reflection from bodies that are located much further away from the radar set than the wavelength used and that are much longer than the wavelength of the radar used. A geometrically flat plate can only backscatter in the direction perpendicular to the surface. Reflections from all other directions occur, but they do not propagate back to the monostatic radar. The 4 pi in the equation arises because a sphere is defined as a reference. A cylinder has the advantage over a simple plate that a backscatter can now be received in an entire plane perpendicular to the height. With a sphere, it does not matter from which direction it is illuminated. It offers identical conditions in all directions. As long as the diameter is also significantly larger than the wavelength, the sphere is also frequency independent. It is, therefore, ideally suited as a reference. From a far distance, an observer does not see the spherical shape but a surface with the diameter of the sphere. However, only a very small part of this spherical surface, shown here in red, is effective for backscattering. Isotropically reflective does not mean that this sphere would distribute the power arriving from one direction equally in all directions. The shape and size of the distribution are different but always the same relative to the aspect angle of the illuminating radar, regardless of the angle from which the radar illuminates this sphere. The diameter of the sphere must be approximately 1.23 meters for an area of 1 square meter. Unlike the isotropic antenna used in antenna calculations, an isotropic reference reflector can be constructed in reality. However, it would be bulky due to its size. In a measurement setup, a calibrated corner reflector can also be used because the radar's direction and its transmitter's frequency are approximately known. A corner reflector consists of 2 or 3 electrically conductive areas that are positioned at an angle of 90 degrees to each other. If the edge length of the corner reflector is significantly larger than the wavelength, then the effective area can be calculated according to the laws of geometrical optics. All parts of the incoming planar wavefront travel the same distance during reflection. As a result, a planar wavefront is backscattered in the identical direction. The trihedral corner reflector consists of 3 metal sheets welded at a 90 degrees angle. The shape of the sheets can also be rectangular or rounded instead of triangular, but then other equations apply. Multiple reflections cause the incoming wave to be backscattered exactly in the same direction from which it arrived. The reflector is most effective when the incoming wave sees 3 equally sized partial areas. The peak bore sight direction is the line with an angle of 45 degrees to all 3 plates. This means that this corner reflector is direction dependent. The half-power beamwidth of the retroreflection diagram is about 40 degrees wide. Because the size of the reflector is measured as a ratio to the wavelength lambda, the size of the radar cross-section is frequency dependent. A trihedral corner reflector with an edge length of equals 15 centimeters has a radar cross-section of 2.128 square meters in the X-band. This means that an isotropic spherical reflector, the reference, would have to have a diameter of 1.65 meters. In comparison, such a corner reflector is much more practicable. The echo signal of an aircraft is composed of various individual components. Diffraction occurs mainly at sharp edges and corners, in addition to specular reflection. First, tip diffraction. Scattering from tips is less significant than specular echoes. It tends to increase with the square of the wavelength, not the size of any surface feature. Second, specular surface return. A specular scatterer is any target surface that is oriented perpendicular to the line of sight to the radar. Flat surfaces offer particularly large echoes in the specular direction, but the echoes drop off sharply away from that direction. The specular echoes from singly and doubly curved surfaces, cylindrical and spheroidal surfaces, are somewhat lower than those from flat surfaces but are more persistent with changes in aspect angle. Third, creeping wave return. A creeping wave gets bound to a smooth, shaded surface. It is guided around the rear of a smooth body and is then launched back to the radar when it reappears at the shadow boundary on the opposite side. The creeping wave mechanism is significant for military and civilian targets only at low frequencies. Fourth, edge diffraction. Like scattering from tips, the scattering from edges is less significant. They become progressively less important as the radar frequency rises. This also applies to the corner diffraction, of which only 1 of 5 is marked here. Sixth, traveling wave echo. When the angle of incidence is a small grazing angle off the surface, a surface traveling wave can be induced. The surface wave tends to build up toward the rear of the body and is usually reflected back toward the front by any discontinuity at the rear. Traveling wave echoes at low grazing angles are nearly as significant as specular echoes at normal incidence. 7th, interaction echo. Relatively strong echoes can occur when a pair of target surfaces are oriented for a favorable bounce from one surface to another and then back to the radar. We have already studied a simple principle with the dihedral corner reflector. However, far more sources of backscattering can occur in the interaction echoes. 8th, gap or seam echo. Most airframes have slots or gaps where control surfaces meet the stationary airframe. Slots, gaps, and even rivet heads can reflect energy back to the radar. 9th, cavity return. Multiple reflections can also occur in cavities such as the inlets of the engines, a transparent redome, or the windows of the cockpit. A characteristic Doppler frequency can then be generated by the compressor blades in the engines. 10th, curvature discontinuity return. Waves are also scattered by discontinuities in slope, curvature, etc. All parts of the reflected or scattered energies have a different distance to the phase front. All depend in varying degree on the target aspect angle as seen from the radar. This results in different phase positions due to the runtime differences. These individual parts can either subtract, destructive interference, or add, constructive interference. Another aspect angle of the same aircraft results in other distances and thus other interferences. This means that the amplitude of the echo signal fluctuates considerably even with very small changes in the aspect angle. These fluctuations can be in the range of 30 decibels. Due to the large number of influences on the result with complex surfaces, these fluctuations can only be analyzed statistically as a probability distribution. Probability distributions are typically defined in terms of the probability density function. These fluctuations of the radar cross-section were mathematically analyzed by Peter Swerling in 1954. The Swerling models describe the statistical properties of radar cross-sections of objects with complex surfaces. According to the Swerling models, the radar cross-section of a reflecting object is based on the chi-square probability density function with specific degrees of freedom. The chi-square distribution results when independent variables with standard normal distributions are squared and summed. There are 5 different Swerling models, numbered with the Roman numerals 1 through 5. Swerling Case 1. The target consists of a number of equally large isotropic reflectors that are distributed on a surface, view A. Another aspect angle of the same assembly, view B, results in other distances and thus other interferences. This case describes a target whose magnitude of the backscattered signal is relatively constant during the dwell time. It varies according to a chi-square probability density function with 2 degrees of freedom, m equals 1. The radar cross-section is constant from pulse to pulse but varies independently from scan to scan. The density of probability of the radar cross-section is given by the Rayleigh distribution. Cases 1 and 2 characterize the statistical behavior of echo signals from aircraft. Case 1 is for a rotating omnidirectional search antenna, and Case 2 is for a target tracking radar focused on a target. The equations are identical, only the time sequence of the scans differs. Cases 3 and 4 describe the behavior of targets in which a larger retroreflective surface is superimposed on several smaller ones or in which a large retroreflective surface slightly changes its aspect. They should apply to ships. Again, the difference between cases 3 and 4 is an observation of either a surveillance radar or a target tracking radar. Case 0, or Case 5, is the reference case with no fluctuation at all. So far, we have assumed that the reflecting surfaces are much larger than the wavelength of the radar transmitter. Artillery shells or simply raindrops can also be equal to or smaller than the wavelength. Two main effects occur here: specular reflection and the creeping wave. However, the addition is phase-dependent. A phase jump of 180 degrees occurs during specular reflection. The phase of the creeping wave must also have this 180 degrees or additionally plus n 360 degrees for constructive interference. This means that the ratio of the circumference or radius to the wavelength is decisive for constructive or destructive interference. In the first case, the radar cross-section increases approximately linearly with the circumference. This area is called the Rayleigh region. The Rayleigh region is applicable predominantly for precipitation radar. Strong interference then occurs. This region is called the Mie region. In aviation, the Mie region can apply to VHF radars. If this interference is less than 10%, the situation changes in the optical region. This applies to most air defense and security radars. These examples given are measured in X-band and are shown here on a logarithmic scale. The auxiliary unit of measurement is decibels per square meter, dBsm. The smallest objects detected by radar are flying insects. For example, a honeybee with -45 to -40 dBsm. Sensitive radar sets are mortar radars. An artillery shell has a radar cross-section of -40 to -35 dBsm. The F-22 Raptor fighter aircraft is also up to -33 dBsm in this range. In contrast, a Tomahawk cruise missile would offer a huge area of -3 dBsm. That is as much as a shepherd dog. In between are birds and quadcopters in the -17 to -15 dBsm range. A person has about 1 square meter, corresponding to 0 dBsm by definition. Incidentally, female persons can have up to twice this area, which is due to pieces of jewelry such as rings, necklaces, and earrings. A passenger car or a small helicopter has between 3 and 5 square meters. That is 4.8 to 7 dBsm. A large transport aircraft has 80 to 100 square meters, corresponding to 19 to 20 dBsm. Large cruise ships top this list with 40 to 50 dBsm. This area can already be calculated as 1 to 10 hectares. The possible applications pursue the goal of either increasing or reducing the radar cross-section. Corner reflectors for remote sensing of Earth are installed on sites to reflect radar signals back to the satellite at specific locations. They are used to acquire displacement measurements over areas that are densely vegetated or covered by snow, monitor specific locations within your area of interest, calibrate the radar receivers in satellite radar. The edge length A is equal to 1.5 meters. This corner reflector has a radar cross-section of 75 square meters at a frequency of 1 GHz. Corner reflectors give inflatable dummy tanks a credible signature, even for radar. The escort ships for an aircraft carrier use corner reflectors to be displayed on the radar screen just as large as the more important target, the aircraft carrier itself. An airplane can pull a corner reflector on a rope behind it for self-protection. Anti-aircraft missiles with semi-active radar control will then engage the stronger target. Although there are also efforts to apply stealth technology to warships, most civilian ships strive to be seen to avoid collisions. Smaller boats in particular therefore carry any corner reflector. Obstacles, such as buoys, also contain corner reflectors. In military technology, exactly the opposite is sought: the smallest possible radar cross-section. Stealth technology, also known as low observable technology, LO technology, is a sub-discipline of military tactics and passive and active electronic countermeasures that encompasses a range of methods used to make people and equipment less visible, ideally invisible, to radar and other detection methods. Although specific details concerning stealth technology are classified, some general information is known. For example, surface materials and coatings can absorb radar transmissions, reducing reflections to an enemy's radar receiver. This is known as radar-absorbing materials, abbreviated RAM. The typical right-angled arrangements of reflective surfaces must be consistently avoided. The surfaces must be straight and scatter the incoming waves in a different direction than back to the illuminating radar. Minimizing shapes and corners. Reflections are reduced using smooth, rounded shapes instead of sharp edges and points. The engine openings must be positioned so that the radar does not detect the engine blades. But all these measures only work if the wavelength is significantly smaller than the surfaces. Stealth technology is ineffective for very long-wave radar sets. This has led to a renaissance of VHF radar sets. As befits any publication, I have also listed the sources for the content here. Thank you for your attention.